15, I got here early.
All right, we're gonna go ahead and get started here. I don't wanna take up any more of your time and, so the purpose this morning really is to give you the opportunity to. I have no idea if I just ended my own YouTube stream or not, but we'll see. I'll find out later. So what we're gonna do is, I'm giving you an opportunity to ask questions, go through some things. And if we don't have questions and we just want to just do some practice problems and things, I've got, we can pull the Kahoots here and kind of play a review game, or we can go through the final exam prep questions that are on Blackboard, and that's completely up to you how we proceed from here. But the next hour 45 is your time here, so I'm gonna let you kind of drive the bus and tell me what we need to talk about. Sure. Okay, so we'll start here at the beginning. We may not go through every single question because that will probably take more time than we need. But let's just start at the beginning here with exam 1. And so if you're unfamiliar, all that you need to do, either scan that QR code or go to kahoot.it and drop in that game pin, and we'll get started. Okay, so this is exam 1 material, but these are ACS practice test questions from chapters 1, 2, and 3. And so here would be the first one. An atom of strontium-90 contains which of the following? You did it in the past. Yeah. I don't know about Harvard. No, Harvard. That only one person had one for that. Like, it's not everybody. Okay, most of us are correct here. What we have to remember is, what does it mean when we describe something in this way as say, strontium-90 or as anything else for that matter. And what we have to remember is that that 90 is the mass number. Mass number being the number of protons plus the number of neutrons in that nucleus. So if I go to my periodic table, strontium is element number 38. So I know from this that there are 38 protons. And so 90 minus 38 would be how many neutrons there are, which would be 52. Since this is a neutral atom, not an ion, then it's safe to assume that the number of protons and the number of electrons is the same, which is why those three here all have that matching kind of feature. So that's the thing that we have to kind of walk away with out of this opening example is we just got to go back and remember some of those terms, some of the ways that we described and referred to atoms early on here. It's on the smaller side here. We're looking at three different isotopes: neon 20, fluoride 19, and the magnesium ion 24. Okay, so we have three different elements here. We know that the number of protons cannot be the same. They're three different elements. The thing that makes an element is the number of protons. So the fact that they're all different elements, they all have the different numbers of protons. So what it comes down to then is, okay, well, if they have different number of protons, maybe they have the same number of neutrons. Well, this is neon 20. So neon 20, 10 protons, 10 neutrons. Fluorine 19, 9 protons, 10 neutrons. That's not bad. Magnesium is 12. Oh, that's wait. 12 protons, 12 neutrons. That's not going to work. So it's not the number of neutrons. Maybe it's the number of electrons. Neon has 10 protons and 10 neutrons and 10 electrons because it's neutral. Fluorine, 9 protons, but with an extra electron for the charge, that makes 10 electrons. Magnesium, 12 protons, but 2 extra compared to electrons, so 12 minus 2 is 10. So all three of these have 10 electrons. So that's why the yellow is the correct answer there. All right, good. We remember what isotopes are. Same chemical element, but different nuclear makeup. So the two different uraniums would be isotopes of each other. So we're talking about this is the famous gold foil experiment. This is out of atomic theory, and so this was not something that we covered explicitly in lecture. It was in your chapter 2 reading. And what we want to talk about here is, okay, so we've got this gold foil. We're shooting these alpha particles at it. The alpha particles are big. As far as radiation goes, alpha particles are basically helium nuclei. So we're shooting helium atoms at this piece of gold, and the majority of them are going straight through the gold. But some are hitting the gold and getting deflected at these large angles. So of these, the biggest takeaway from Rutherford was this, yellow. The atoms were mostly empty space. Why are they mostly empty space? Well, the big heavy particles are going straight through the foil. If the gold was as dense as we thought it was, then all of those particles should have shot back, because gold is so much heavier and more dense than helium. But the fact that the majority of them are going through tells us that even though the gold is a dense and heavy metal, the majority of the space that it takes up is actually empty. It's not truly empty, it's electrons. But relative to an alpha particle, an electron is but a measly flea. All right. Any questions with what we've seen so far? Atom has a valence shell electron configuration of ns1. To which group does it belong? Yeah, so what we have to remember here, N is just the energy level. So we're talking about 1s1, 2s1, 3s1, 4s1, that being the last configuration of that particular element. That's column 1. Column 1 is known as the alkali metals. In which case is the energy of the photon the greatest? So we're on the right side of the spectrum, at least. X-rays and UV are the two most energetic types. What we have to remember is X-rays and cosmic rays are basically the highest. Gamma rays, that is the highest end of the scale. The lowest wavelength, highest frequency light. When we get to visible and IR and radio, that's the low end of the spectrum. That would be long wavelength and low frequency. Which of the following ground state configurations is possible for an element in the second period? Okay, mostly on the right track. So the things that we have to remember that for the second period, we would only have n equals 1 and n equals 2, which all of these cover. And that in n equals 2, for ground state, that is the lowest energy configuration, the only possibilities would be the S and the P sublevels. So we can eliminate this one here because there's no such thing as the 2D. And the reason this one and this one don't work is because they would represent excited states, where we would expect that the electrons are going to fill the S sublevel first. And the reason we would expect that is because the S sublevel is of a lower energy than the P sublevel. So while this one is on the right track, this second electron wouldn't go here. It would go in that S sublevel because that would be the lower energy configuration for beryllium. This represents an excited state where one of those electrons has moved up to the p orbital because it's gained some amount of energy. And we would see the same thing here. We've skipped the S and gone straight to the P. That's not the correct order of things. So while all three of these are possible, this one is impossible. While all three of these are possible if we consider excited states, since we're being asked about a ground state, it has to be yellow. The number of unpaired electrons in gaseous selenium is what? Now, this is a great place to get bogged down into unnecessary details. Does it truly matter that the selenium is gaseous? Not at all. Why we say that? Well, usually when we're looking at electron configurations, especially for ionization does tend to happen at that gaseous form, but in this case, it does not matter. What we need to do is, if we're looking at selenium's electron configuration would be, we'll just use the noble gas configuration here, argon 4s2, 3d10, 4p4. Now, the reason we can do that is because since we're being asked about unpaired electrons, we know that all of the core electrons, the ones represented by argon here, are all going to be paired up because all of those sublevels are filled. And we know that this sublevel is filled, so everything's paired. This sublevel is filled, so everything's paired. The way to answer this question is we look just at that 4p sublevel, and we can draw an orbital diagram real quick and put in our 4 electrons and recognize off of that orbital diagram that these 2 electrons here are unpaired, which gives us red triangle 2 as the correct answer. So in questions like this, it can be really tempting to look at, okay, well, the only way to know that it's an unpaired electron is to look at an orbital diagram. And you get tempted to make the entire orbital diagram. But in reality, the only part of this that you need for orbitals is just that last part of the configuration. All right, questions here? All right, which electron transition in hydrogen would have the largest emission? Ooh, very split. Okay, couple of things here. First of all, we should have been able to eliminate almost immediately half of the responses. Because if I'm going from 2 to 4 or from 2 to 3, the result is not going to be an emission of energy. It's going to be an absorption of energy. Energy is going to have to be drawn in to get that electron to go up to the higher energy levels. So these are absorptions, not emissions. So we can eliminate those 2 options right off the bat. Since we're being asked about the largest emission, now we start to look at, okay, well, what kinds of emissions are there? Well, we're going from 2 to 1 and from 3 to 2. Well, that doesn't help us a ton. They're both 1 energy level apart. What we have to understand is that the energy levels are not evenly spaced. So I imagine that this is my nucleus here. Here's my first energy level. What we have to understand is that the spacing gets tighter the further away from the nucleus that we get. And so the biggest gap in energy is going to be the one that is the closest to the nucleus. That's why A, red triangle, is the correct answer. As you get further from the nucleus, the energy gets closer and closer together, which is why we don't define the nucleus based upon, or we don't define ionization based upon a certain energy level. If you remember, we talk about something called the infinity energy level. What is n equals infinity? All that we know is that that's when the electron's gone. We don't know necessarily if it's n equals 17 or n equals 20 or n equals 25 or whatever. We just know that at some point, the electron is no longer in the atom. It's now outside of the atom. That's what ionization energy is. How much energy does it take for that electron to get promoted to a high enough energy level that it's no longer in the atom itself? Yeah. This one should have been simple, and it was. The key here was the atomic number 24. You go to the periodic table, 24 is Cr. Cr is chromium. You all had that one. Okay. What best describes the relationship between hydrogen and deuterium? Probably a better question. Do we know what deuterium is? Okay. Now, 4 of you have already answered, so for those of you that guessed wrong, you'll have to kind of live with that. So deuterium is when we describe something as hydrogen. Almost impossible. When we describe something as hydrogen, that's what we usually think of. Hydrogen is a single proton in a nucleus with one electron going around it. As an element, hydrogen exists as H2, where those two unpaired electrons link up and make a single bond. Deuterium, if you know anything about Greek and Latin roots, deutero is a form of 2. So what are we referring to as 2 here? 2 would be the mass number of deuterium. And then there's a third version of hydrogen called tritium. And you can kind of figure out what that one looks like. Tritium tri, we're talking about 3 as its mass number. Now, knowing what these are now, you can come up with the fact that you recognize that those are all isotopes. They're all the same element, they just have different mass numbers. So this is more of a question of, do you know what deuterium is more than anything else? All right, we've got our first math problem. Element X is naturally 20% X12 and 80% X13. The atomic mass of X is nearest to which?
I already know it's small. Everything's going on my phone. So that's fine. That's fine. I want to.
Okay. So we're all on the right track here. Now, here's the thing with this question. And one of the things I was saying yesterday in the review session was be aware that sometimes the math problems are not all that mathy, and that there are usually things built in that can kind of clue you into what the correct answer is without actually having to pick up your calculator. If you understand the basic concept of percent by mass and how we calculate atomic masses, you know that what we needed to do was you needed to take the 20% of 12 and add it to the 80% of 13. And if you had done that, then you would have gotten 2.4 here and 10.4 here. And if you add those together, you get 12.8, which was the correct answer. But you could have also worked this through pretty logically. The abundance is favored pretty heavily toward the 13. So we know that the answer isn't green. It can't be 13 itself because unless it's like 99% 13 and 1% 12, we're going to dip down below the 13 pretty significantly. We also know that it's not heavily skewed toward 12, so that one can't be correct. And this one would only be correct if it was 50-50, and it's not. So we can make a pretty logical argument that it's yellow circle just based off of the numbers that they've given us without actually picking up the calculator and doing it. Now, did it cost me a ton of time to pick up the calculator and do it? Not in this case, no. But in an exam, and this is the thing that you have to recognize about the ACS exam, they are giving you 110 minutes to do 70 problems. So you do a little bit of quick math and you go, holy crap, that's 90 seconds per question. How are you supposed to do it? And the answer is you're not. The 90 seconds per question, that's an easy way to get yourself messed up. Chances are pretty good that a lot of the questions are going to be ones that you can answer in way less than 90 seconds. Those isotope questions, for example, you can probably knock those out in about 8 seconds. But the other half of it is that recognize that you have to actually have time to do the work. A lot of the calculation-based questions get simplified and, for lack of a better term, stupefied so that the math is a lot easier than you think. Either because they give you answers that are absolutely impossible, or they do things like this where you can kind of logic your way to the correct answer without actually having to do the calculation itself. Okay, coming back to isotope and isoelectronic. So we have to understand what both of those terms mean. Okay, so first and foremost, I would look at the term isotopic. Isotopic means I've got to have the same element. Right away, we can eliminate that first option because we've got two different elements there, so it can't be isotopic. What we have to remember is isoelectronic means that it has the same number of electrons. The only way that you can have isotopic species that are also isoelectronic is that they have to have the same charge. And so you start looking at the charges here, and the only one that has matching charges is the blue diamond, because both of those potassiums are +1 in charge. How many electrons can occupy a dxy orbital? Okay, caught a couple of you. Didn't read the question correctly. Okay, let me ask you this. What if the orbital was a p sub x orbital? How many electrons, how would the answer change there? What if it was a 4s orbital? How would the answer change there? The key word in this problem is orbital. Orbitals can only hold 2 electrons. It doesn't matter what kind of orbital they are. So now if it was asking you about the d sublevel, green would be the correct answer. The d sublevel holds 10 electrons. But it wasn't asking you about the sublevel. It was asking you about the orbital itself. And the orbital can only hold 2 electrons. All right. Ground state electron configuration that looks like this. What is it? Okay, we're all over the place. Okay, so I can understand why you might take yellow circle here. You looked at that 3D10 configuration and said, okay, the last configuration in zinc is 3D10. That must be the correct answer. Problem is you didn't read the configuration fully. Before you get to the 3D sublevel, you have to occupy the 4s sublevel. So the configuration for zinc is argon 4s2 3d10. This is my argon. I'm missing the 4s2, so zinc can't be right on its own. Now for nickel's configuration would be argon 4s2 3d8. So that's not correct either. So maybe that makes you say, okay, well, what about nickel 2 plus? Nickel 2 plus would add 2 electrons, right? No, that's not what 2 plus means. 2 plus means that we've lost 2 electrons, not gained 2 electrons. In the case of, so this is nickel. In the case of nickel 2 plus, we're going to lose those 2s electrons. It's going to be argon 3d8. In the case of zinc 2 plus, we're going to lose those 2 electrons. It's going to be argon 3d10. which happens to be the thing that we're looking for. So green square was the correct answer here. We were looking ultimately for that configuration, the 3D10. So that gave us a zinc 2 ion. Okay, chances are pretty good you're not going to be able to answer this question without context. Paramagnetism, not something that we talked about explicitly as a atomic property. When it comes to paramagnetism, the term here, looking for unpaired electrons. That's what we're looking for. We're looking for unpaired electrons in this arrangement. So what does that mean? So I gotta look at each of these electron configurations and figure out where are there unpaired electrons possible. Now we just talked about zinc. Zinc is argon 4s2 3d10. Every one of those sublevels is completely filled, so all the electrons are all paired. So that's not going to work. The term for something that is not paramagnetic is diamagnetic, where magnets go to die. And so since zinc is diamagnetic, we can eliminate green square, we can eliminate orange or yellow circle. Now we just need to look at the iron 2 and the tin 4. For iron 2, our configuration was argon 4s2 3d6. So iron on its own has a good bit of paramagnetism. But for iron 2 plus, we're going to take these 2 electrons away. And so I look at the configuration for the iron 2, and I see 6 electrons. 4 of those electrons are unpaired. So we know that iron and iron 2 are both paramagnetic. For titanium 4, titanium's electron configuration is argon 4s2 3d2. For the 4 plus charge, I need to take away 2 electrons, 4 electrons. All that is left is the argon. We know that they're all paired up. So titanium 4 is diamagnetic, which means that this one's incorrect. Only the iron was. So red square wins that one, or red triangle, rather. Okay. So when I told you yesterday that there's nothing on this exam that you haven't seen, that's mostly correct. You should be able to at least have a good, educated guess at every single question on there. Now, there are going to be a couple of questions. I know there's one question on there that uses molecular orbitals. And you can kind of reason your way through it. I know there's questions like this pop up from time to time. These are just little kinds of things. And again, what I told you yesterday about the exam is absolutely true. They are really trying to test your problem solving skills. They're trying to test your critical thinking skills. They intend for you to miss a couple of questions. So if you see a question like this, don't get discouraged by it. You know, take your best stab at it and move on to the next one. See what's the next one here. Okay. I'm going to lay out here and let you just kind of see if you remember what I said about 15 minutes ago about energy levels. Okay, so you had to put together a couple of concepts here. First of all, frequency and energy are directly related. So the energy gap that is the biggest would also give us the highest frequency light. That was the first thing that you had to put together. Second thing you had to put together was keeping that in mind. When I told you a few questions ago, I drew you that energy level diagram. The gap between the lower energy levels is greater than the higher energy levels. So your face should have been drawn to these early energy gaps, and 3 to 1 would be the biggest gap of them all, even though they're all only 2 energy levels themselves. And so in the interest of, oh, we'll do this last one because quantum numbers always throw you for a loop. This will be the last question that we do out of this exam. We're at 10 till 11 right now. I want to make sure I get a chance to go through some of the other exam material because those are the ones that you struggle with more. Okay, half of you there. Most of you are on at least somewhat of the right track. So what we have to remember are the rules associated with these quantum numbers. So L can go from 0 to n minus 1. Since n is 4 in this case, we can go from 0 to 3. And so that invalidates blue all automatically because L can't be equal to n. For m sub L, we are allowed to go from negative L through 0 to positive L. And so we want to start looking at our options and seeing, okay, if given the L, does the m sub L make sense? So in the red one, it does. In the yellow one, it does not. L's 2, so m sub L can't be 3. In the green one, it makes sense. And then for the spin quantum number, it has to be either positive or negative 1/2. And so that's why green is incorrect. You can't have a spin quantum number of 1. So red triangle is the only possible answer. It's also the correct answer. And so when it comes to quantum numbers, this is the kind of question that you should expect to see if you're going to be evaluating those quantum numbers in some kind of way. All right, any questions out of the exam 1 material before we move on to something else? So let's move on to number 2 then. So questions in this one are going to be mostly out of solutions and stoichiometry, going to be a lot more calculation oriented here. So go ahead and get signed in. Okay, empirical formula question. 54% sodium, 8.5% boron, 37.5% oxygen. What is the compound? So if you're having trouble remembering what to do here, remember, we're ultimately looking for the chemical formula here. And so the easiest way to go about that is to take these percentages and turn them into grams of each individual element. And since what we're ultimately looking for is a ratio between them, we need to convert each of them into moles so that we can compare their atomic ratios on even footing. So one trick that you can use is these are going to be expect the numbers to be extremely clean. And what I mean by that is expect that the numbers are going to be such that it's pretty easy to figure out what it is that you're doing here. So I have pestered you for 4 months about significant figures. This is the time to take that information and largely ignore it. And take some shortcuts. So, the periodic table says that sodium is 22.99. That's close enough to 23.0 that we can slide around that one. Boron's 10.81. Let's just call that 10.8. Oxygen is 16.00. Let's call that 16. And so if I take 54 divided by 23, I get 2.35. And if I take 8.5 divided by 10.8, I get 0.78 or 79. And if I take 37.5 divided by 16, I get 2.34. And so right away, again, the point isn't necessarily to get the correct answer, but to get the correct answer quickly. And so one thing that you can do to help you eliminate options is you should recognize out of this, okay, sodium and oxygen, they're the same. So any answers where sodium and oxygen are different automatically can be removed. So I can eliminate blue, I can eliminate green, because sodium and oxygen are different numbers in those. Now in between yellow and red, how do I know which one's which? Well, this is where the other part of it comes in. I need to divide by 0.79 to figure out the ratio. That's going to give me 1 boron. That's going to give me roughly 3 sodiums. Now, since I know sodium and oxygen are the same, I don't need to do this calculation here. I know they're the same. And so 3 sodiums, 1 boron, 3 oxygens, that's red triangle. So one of the hallmarks of this kind of exam is efficiency. Don't take extra time doing things that you could do in simpler steps. You can recognize certain little things like that. Even if you make the next step incorrect, it's a lot easier to guess on a 50-50 than it is to guess on a 1 out of 4 or a 1 out of 5. So look for those little places where you can save yourself time, where you can kind of steal a minute from the test makers by recognizing certain kinds of attributes of the question. What was the percent mass of oxygen in iron 3 sulfate? Couple things to look at in this one that would be helpful. How many oxygen atoms are we talking about in this compound? 12, because there are 3 sulfates and 4 oxygens per sulfate. So automatically right away, your brain should be going toward, this is going to be one of the bigger numbers because there are more oxygens in this compound than there are any others. And it's not like oxygen has the mass of hydrogen or something like that where it's going to kind of get weeded out that way. We've got a massive amount of oxygen relative to anything else. And so for setup, we know that we need the mass of oxygen divided by the molar mass. Mass of oxygen would be 12 times 16 grams. And the molar mass would be that plus 3 times 32 and 2 times 55.85. So 12 times 16 is 192. If I add to that 32.07 times 3 and 55.85 times 2, I get 399.91. And so, yeah, 192 divided by 399.81 is 48%. So green square would be the correct answer there. Again, from a logical standpoint, I'm going to look at this and go, boy, that's a lot of oxygen. My guess, if I had to make one, let's say that, Dr. Bruck calls 10 minutes left on the exam and I have 10 questions left. And I'm trying to busy my way through to make sure I finish and get an answer in for everything. And by the way, make sure you get an answer in for everything. There's no penalty for having a wrong answer there any more than there is for having having a blank answer. So you might as well try everything because your overall score is based on how many you get right. You can't get it right if you leave it blank. But if I'm looking at this and going, okay, I only have a couple of minutes left, what seems to be the most logical choice? Automatically, you should be looking at that and saying, okay, that's probably the biggest component. And so it's going to either be the yellow or the green. It's either C or D. And you can make an educated guess from there. All right, we've got a silicon chip. Has a mass of 2.3 times 10 to the negative fourth grams of silicon. How many atoms are in that chip? Now, just a word of warning, on the ACS exam, they are not going to use the E notation for scientific. I'm using it here because the Kahoot doesn't allow me to do subscripts and superscripts. Trick to this question is knowing what it is that we have to use, what it is that we need. So, first inclination, green square should have come off of your possibilities almost immediately. You know that Avogadro's number is 6 times 10 to the 23rd. And that's if I have 1 mole of silicon. Well, I know that 1 mole of silicon is 28 grams. I've got something that's way less than 1 gram. So automatically I know that I'm not going to be exceeding, because this is something on the order of like 1,000 moles of silicon. We don't have that. So it becomes just a matter of, okay, well, what is it? So 28.1 here, Avogadro's number here. And so another trick that you can use, something that can be really helpful here. Again, let's talk about ways that we can skip out on doing the calculation, doing the math. We know how exponents work, right? I take 10 to the negative fourth and multiply by 10 to the 23rd. The result is going to be something along the lines of what happens when I add those exponents together. Well, 10 to the negative fourth and 10 to the 23rd is going to give me 10 to the 19th as a result. And that's before you even divide by the 28. So again, logically speaking, once I've done this setup, I can look at the exponents here and go, okay, the only exponent that makes sense is this one. Can I do the math and verify that? Yeah. 0.3 times 10 to the negative fourth. times Avogadro's number divided by 28.1. Yeah, I get 4.9 times 10 to the 18. But my point is, again, logically speaking, I'm just applying some general exponential rules, and all of you in here are taking, at the very least, college algebra. Half of you in here are taking calculus. If you understand that rule from calculus, why not use it here? Here we have a stoichiometry question. Right, so we're being asked to do basically the gram to gram, mass to mass stoichiometry here. So we're starting with 1 gram of the Freon 12. The first thing that we want to do is we want to convert that grams into moles. So I went ahead and calculated the molar mass. Molar mass is 120.9. So my grams cancel. My next step was to convert the moles of the Freon into moles of the antimony trifluoride. Now that was not a 1-to-1 ratio. probably one of the most common mistakes students make is just assuming that it is. Okay, I got to pull the numbers off of the balanced chemical equation. Balanced chemical equation shows me that it is a 3-to-2 ratio. So 2 antimony to 3 freon. And then the last step would be to turn the moles of the antimony trifluoride into grams. For that, you need the molar mass again. So if you do this all the way across, 1 times 2 times 178.76 divided by 120.9 divided by 3, you end up with 0.986 grams, which was the blue diamond here, and half you got to that. This is one of those questions where you're gonna have a very difficult time trying to kind of logic and reason your way through it. Because there are too many numbers to consider here. You've got to consider the molar masses, you've got to consider the mole ratio. So this isn't one of those where you can just kind of stare at it and say, it's probably C or D, because it would have to be a pretty big number. Can't do that here. That mole ratio really does a number on that kind of logic. Yeah, if it's 1-to-1, make those logical leaps. It's a lot easier to do so. You can compare the molar masses and say, okay, well, this molar mass is about 1.5 times bigger, so my answer should be about the same. But if that mole ratio is anything other than 1-to-1, you gotta go through the calculation. And unfortunately, there's not really a shortcut for that. So this is one of the ones where, all that time that you've been banking because you've been, going through and doing your other ones efficiently, this is where that time goes. It goes to questions like this. All right, questions with it? This is one I talked about is actually considerably easier than you think. So I'm going to talk about today in class. The thing that you want to look at is, so carbon dioxide goes straight to carbon, water goes straight to hydrogen. Now, here's where recognition comes in. You've done a lot with water, you've done a lot with carbon dioxide over the course of this semester. What's the molar mass of water? 18. 16 for oxygen, 2 hydrogens, 18 total. So I look at this first number here for the water, 0.18 grams divided by 18 grams per mole. My eyes light up because I go, that's 0.1 moles of water, which means that's 0.2 moles of hydrogen. Because again, the whole point is to figure out how much hydrogen there is. What's the molar mass of carbon dioxide? 44. 12 for the carbon, 32 for the oxygen, 44 in total. So I've got 0.44 grams divided by 44 grams per mole. That's 0.1 moles of carbon dioxide, which would be 0.1 moles of carbon. Now I've got my ratio. Carbon 0.1, hydrogen 0.2. I recognize that they are a 1-to-2 ratio of each other. I look for the compound that is also a 1-to-2 ratio. This is an example of a problem that is designed to look incredibly difficult, but they usually give you compounds where the molar masses are not only well known, but if they're not well known, they divide incredibly easily into this. If it wasn't that way, the stoichiometry for this would be, half a page long. But they're giving you that information so that it's easy to see what it is that you need to do. So be on the lookout for that kind of thing. If a problem seems like it is extra complicated, calculate that molar mass, see if the answer is hidden within the text. Chances are it probably is. We got a 17-gram sample of impure nickel reacting with excess carbon monoxide to form 6¼ liters of tetracarbonyl nickel gas complex under STP conditions. And what we want to know is, what is the percent of nickel in the impure sample? Okay, lots of pieces and parts in here. What's the main takeaway? We need to convert liters of the product into moles so that we can convert it into nickel. And then we can compare this nickel to this nickel to figure out what percent it actually is. Now, the trick to this is that we are under STP conditions. And so what the exam writers want you to do is they want you to recognize that it's STP, and instead of using the ideal gas law to figure out the number of moles, what they want you to do instead is they want to use the conversion. 6.25 liters at STP, 22.4 liters in 1 mole. And then we can go from here. 1 mole of the nickel complex is 1 mole of nickel metal. And 1 mole of nickel metal weighs 58.7 grams. So this amount of product came from 16.4 grams of nickel. Do you need to do the math from here to figure out the percentage? Pretty close. So we know it's not 100% because then it would be 17 against 17. But we're talking about 16.4 against 17. That's the yellow circle, 95%. Could you do the math to be sure? Yeah. But of the other options, it's the only one that makes sense.
I don't know, I think borderline journal.
So look out for those little kinds of context words, like STP, or I'm under ideal condition. Those are going to kind of tell you clues about what it is that you can do and what you're allowed to do. Because if you can save yourself the mess of having to use the ideal gas law just to get the stoichiometry started, you're going to save yourself a ton of time. Now, clue you in on something else. Again, the writers of the exam know what kinds of time constraints they've put you under. They're not going to write a whole lot of questions that involve multi-step, complicated calculations that get you to go. If you see an ideal gas law kind of question, it probably is going to be just that, an ideal gas law kind of question, not one that's hung up on stoichiometry as well.
What would be the best way to get this problem?
Well, if you're going purely for guess here, I mean, what I would do is automatically I would eliminate green. The fact that we're told that it's impure means that 100% can't be correct, because that would be a contradiction. You can't call something impure and then calculate it to be completely pure. That's blatantly false. So my first inclination would have been to be drawn toward the yellow one anyway, just on the idea that, okay, if it's a nickel sample that has at least some purity, that one would make the most sense. But otherwise, if you're guessing, the other thing that you would look at would be, okay, I could use the ideal gas law, and N is equal to PV over RT. I would just have to remember what my STP conditions were. 1 atmosphere, V is 6.25 liters, R is 0.0821, T is 273 Kelvin. And from that, I could calculate whatever this value is, about 0.25. And honestly, speaking as someone who's written some exams before, that's probably the genesis of the blue answer. It's just, that's the number of moles. And so common distractors are steps along the calculation that could be misinterpreted for the correct answer. But yeah, if I took it from there, I could be like, okay, that's about 25%. And I could multiply by the molar mass of nickel and get myself close. So ultimately, it's a recognition kind of thing. You have to recognize that, okay, at STP, these things are true. And if I don't know the 22.4 liters thing, at the very least, I would know, okay, I can plug those conditions into the ideal gas law and figure out the number of moles. And then it becomes a matter of stoichiometry from there. Does that take longer? Yes, but does it get you to the right place? It does.
So it's only 22.4 liters per mole.
Based on the definitions that the ACS is using, yes. Dr. Tarbuck said something about 22.7, or I know we use 22.7 in lab. That's based on the IUPAC definition of STP. Why we can't agree on that, I don't know. For the combustion of 3 grams of C3H8O, propanol, and 7.38 grams of oxygen, how many moles of each reagent, which reagent would remain? First thing that I would do in this particular scenario is I would find out how many moles of each reactant I have, and that would be used to help me eliminate options. So I have 3 grams of the propanol, more mass, 12.01 for carbon, times 3 plus 1.01 for hydrogen times 8 plus 16, 60.11. So 3 divided by 60 is giving me 0.0499 moles. And so right away, off of that answer exclusively, I can eliminate green. The reason I can eliminate green is this is a reactant. So if that's how much I'm starting with, there is no way I can get more of it by the end of the reaction. I'm going to do the same thing with the oxygen, 7.38 grams of oxygen, 32 grams in 1 mole. 7.38 divided by 32 is 0.231 moles of oxygen. And again, that eliminates yellow for me because same logic. I can't gain reactant through a chemical reaction. So just doing that one calculation tells me half the answers are absolutely, completely false. And again, if I'm in that time crunch, those calculations took me roughly a minute to do. That minute of calculation narrowed my search down to half. Now it just becomes a matter of what makes the most sense. Now, to actually solve the problem, I need to convert one of these into the other using the mole ratio to figure out which one's actually limiting. So I'll just choose the top one here because, well, it doesn't really matter. So 2 moles of propanol for 9 moles of oxygen. 0.0499 times 9 over 2 tells me I need 0.224 moles of oxygen. I have that. So oxygen must be in excess, which means that letter A is the correct answer. If it went the other direction, so let's just say that I took the oxygen and converted it, 9 moles of oxygen to 2 moles of the propanol, 0.231 times 2 over 9. I would have gotten 0.0513. I should have recognized this is more than what I have. So again, same conclusion. Propanol is the limiting reactant. Propanol is going to go down to 0. Since it's going down to 0, this one can't be correct. That one has to be correct. And so I didn't actually need to do the subtraction between those two to get this correct answer, I've eliminated all other possibilities. Am I off by a sig fig? Yeah. Does it matter? Not here. There's no show your work. All right, we've got about 10 minutes left. Do we want to keep doing calculations or do you want to take a look at exam 3? 3? Okay, let's take a look at exam 3 then. All right, quickly get in. All right, which molecule has exactly 2 unshared pairs of electrons in the center atom? Now, the thing about questions like these is your first inclination is going to be to draw all 4 of them and see which one comes out that way. Here's where I want you to use your brains though, because there's actually a faster way to do this where you don't have to actually draw anything. Now, I'm going to take it on faith that all of you know how to draw all 4 of them. After all, that is kind of what we spent the better part of a month doing. But the way that we can kind of work our way through this is by looking at valence counts. So that very first step that we do in drawing, where we figure out how many electrons we're talking about. Okay, so boron's got 3 and fluorine's got 7 and there's 3 of them, so that's 24. Okay. Here's what I want you to start doing, at least for questions like this. Now that, if the question asks you something like, what is the geometry or what is the bond angle, you're gonna have to at the very least draw so that you know what the steric number is. But this can still help you out in a lot of ways. And here's what I'm talking about, okay? I've got 24 electrons here that I need to work with. Each one of these bonds from boron is going to feature a complete octet, right? Okay, so how many electrons are sucked up in that bond set to fluorine? 8. 2 from the bond, 6 from the lone pairs. Okay, so I have 3 bond sets, 8 electrons each. That's 24. there are no electrons left for lone pairs on the center atom. So I don't need to know, or I don't need to draw boron trifluoride to know that it doesn't have any unpaired electrons. I can do the same kinds of things with the other ones. NF3, 5 plus 21 makes 26. If I take away the 24 from the bonds, there are 2 electrons. That's 1 lone pair. I need 2. That's the wrong answer. OF2 is the correct answer. 6 plus 14 is 20. Each of those bonding directions is 8. 16, 4, 2 lone pairs are the result of that. That's what we were looking for. For the xenon, 8 plus 14 gives them 22. There would be 3 lone pairs on that. And so you can start to make some preliminary determinations about each of these based on that information as well. Okay, so in the case of NF3, I'm going to have 3 bonding groups and 1 lone pair. That's a steric number of 4. So I'm somewhere in the tetrahedral family, 109.5 degree bond angles. This one is the same. 2 lone pairs plus the 2 bonding pairs, steric number is 4. I'm in the tetrahedral family. What's the difference between them? Well, this 1 lone pair means I'm going to have trigonal pyramidal shape. These 2 lone pairs mean I'm going to have a bent shape. So I can save myself a lot on these kinds of questions by doing this quick analysis. Now, here's where this quick analysis falls apart. It works great if we're not dealing with hydrogen. For hydrogen, we have to remember that it's only 2 electrons for a hydrogen instead of 8. So we have to take that into consideration when we do our subtractions to figure out the bonding kind of scenario. But should work for hypervalent. It should work for pretty much everything except for hydrogen, or the cases where we have odd numbers of electrons, because those won't come out even anyway. Any questions with this? Right, same kind of question. We're talking about a CHCl3 or CH3Cl, I'm sorry, methyl chloride. So if we draw it, this is a case where the adjustment trick really isn't going to save us all that much time. We're going to be able to see pretty quickly what this is. And so I look at this and say, okay, steric number is 4. There are no lone pairs. This is tetrahedral. Need to do anything further with it. Sometimes it is just that simple. Now keep in mind, you're going to be given that chart that equates steric number, hybridization, and shape and bond angle as part of your supplementary material. So again, if you can come up with the Lewis structure relatively quickly, you should be able to analyze it just as quickly and say, okay, I got it. Steric number is 4 here, no lone pairs, that's tetrahedral. Tetrahedral is sp3. sp3 is 109.5 degree bond angles. I can rattle off all of that information in 20 seconds, especially with the chart right there in front of me. And so the beauty of that is that means that from that piece of information, I could pretty much answer any question they asked me. So long as I know how to draw that structure properly, I'm gonna be okay. All right, we'll look at one more. Boron trichloride is planar. Nitrogen trichloride is pyramidal. Which of these is the best explanation for that? All comes down to, if I draw these out, I'm gonna quickly find that after I draw out the lone pairs, I'm not gonna have anything left for the boron, which means that this is going to be steric number 3, which is planar, trigonal planar. But for the nitrogen trichloride, I'm going to have that lone pair of electrons left on there, which is going to give me that 4th steric object and put me into that tetrahedral 3-dimensional geometry. All right, so that's all the time that we have. So just as a reminder of a couple of things. First of all, these Kahoots are available in your Blackboard page. So if you want to come back to them, go back to the ones that we did not look at, you can. If you want to share those to people like Gabe who don't have access to our Blackboard, again, they're fully shareable. The links work. You just need to tap into them. Okay, other things. Those of you that have, is it the physics final that's at 2 o'clock tomorrow? We're going to do 2.
Oh, no, it's 8. I got a fun on both of them.
Okay. Whatever final it is that you have.
Mine's right after my speech. Oh, there. I'll be coming at the.
Yeah, so if you have a final at 2 o'clock and you're worried about getting there on time, like I said, we'll open it up a little bit early so that you have enough time, because our final does get an extra 5 minutes that the school doesn't budget in. Otherwise, open study session here at 10 o'clock tomorrow. It's not going to be a formal session like this. It's just, I'm giving you a place to study. I'll be here if you have questions, but it's not going to be anything formalized or broadcasted. It's just a place for you to study. If you have any questions, you know where to find me. Have a good day.